this is one of the problem that I created from using our emission testing center data set. So we have an emission testing center here. We constantly test engines and we try to find standards for them. So this data was not the exact same data. I had to recode it because it was a confidential engine testing. So I kind of recoded, but the idea is exact same. So what they want to know, these guys send some bunch of engines to us and then test their emission level, and then they want to know from us what they should claim for this engine in terms of different types of emission: carbon monoxide, carbon dioxide. In this case, I have created this data set for carbon dioxide. So the question is, what kind of control charts is appropriate for this type of data? First of all, this emission in parts per million. So this is a variable type of data. So either we can create a R control chart or an S control chart, whatever. If you have a software, it doesn't really matter. You don't do hand calculation anymore, so it takes almost the same time. Either you do R control or S control, and they kind of both provide the same information anyway. So I have created this in Excel, the trial R control chart. If you're not familiar how to create those, check my other videos on how to create trial R control charts. So this is how the data looks like. Now, as you can see, a couple of points at the beginning of the test, something went wrong. We don't know. That doesn't look like belongs to the rest of the data set. So if I go back to the data set again, you can see here. So this is the 40. This is data from 40 different timestamp, one engine, and then 3 samples under each of these timestamp, and then first 3. So that's it. That's how the data looks like. Now, when I created the control chart, I have found these 2 of this data kind of went out of norm. So I thought something went wrong at the beginning. We don't know. It shouldn't belong into these typical characteristics of this engine. So in the revised chart, I have deleted that. Now check my other videos on how to create revise R control charts. So I deleted that. So now this data is kind of standard. I have made any standard by deleting those data, analyzing this, and then found out this is my typical scenario. So the company wants to know what is a standard. So first of all, that's the standard control chart, but they're more interested in what they should be specifying in their engines. So their upper spec limit and lower spec limit for the emission level. Now in this case, this is not the typical situation. So whenever you're trying to design a new product, then you have to find the specification limits. It's not given. So we call it reverse. I call it reverse capability analysis. Check the video on the reverse capability analysis, how to get that. Basically, you're trying to find out this upper spec limit and lower spec limit. So I have calculated this upper spec limit. Check the other video on how this upper spec limit and lower spec limit is calculating. The video is probably says reverse capability analysis or something similar to that, something reverse capability analysis. So check that video how to calculate that. So basically, after doing all this analysis, I have assumed that 1.3 is the standard CP value. So they should be specifying their engine. So this is the upper spec and lower spec for their engine. So the answer to this question would be this. So this is what they should be specifying in their engine. So you buy this engine, you're gonna get maximum emission level parts per million 0.3434, and the minimum emission would be 0.306665. Now once again, even though, and then this question says, even though you maintain this Six Sigma quality control standard, still there will be some engines will be out of spec, because as you know, we have created these standards, and now this data, the normal distribution never touches the x-axis. So if you if you perform this analysis, there will be always some. So if I draw the normal distribution here, it's difficult to draw with my pen. It will never touches the x-axis, so there will be always some area under the. So if this is my upper spec limit, which is 0.3434, there will be always some area right there. So there will be always some engines which will produce more emission level out of the box, just because the random chance probabilistic theory. Now, to calculate that, a lot of time students make this mistake. They try to count the number of data points over that spec limit, which is wrong. So you are just giving the answer based on the sample, but now it's not a sample anymore. After you revise the data, it's become a standard. It becomes the population. I would like to point another thing here. When I asked this question in the exam, a lot of students did not understand what to do with question number 2. It says an appropriate standard control chart. What that means is the revised control chart. So whenever you revise, things get standardized. So you have to use that norm distribution to calculate the area over that upper spec limit. So basically you can do just type, cannot do that much. So basically you can type norm dist equal to norm dist and then x value, we're trying to find the area over that, and then mean, the grand mean, comma, standard deviation sigma, we have calculated that, and then cumulative. Now this will give you area all the way from the left to this point, upper spec limit, but we want area the right side of that area, so right side of that. So this would be probability of x greater than point, I would say upper spec limit. That's what you're looking for here. So this question is asking how many engines will go over this spec limit, even though you are maintaining the 6 sigma. There will be always some area under the curve, even though it's very small, but there will be always some, because this probabilistic world, you cannot say anything 100%. So as you can see here, about 5 engines out of 100,000 will go over the spec limit of the emission level. So I think that's it about this problem.